Hello and welcome to this webinar on distributed fiber optic sensors for dams and levee deformation monitoring. My name is Daniele Inaudi. I'm Chief Technical Officer at SMARTEC and Rocktest. And today I would like to introduce this fiber optic sensing technology that opens new possibilities for monitoring dams and levees. The traditional approach to instrumenting dams and levees is to put sensors at selected locations, for example, temperature sensor or piezometers of strain gauges, and we assume that those locations are representative of the behavior of the dam overall. However, there are sometimes more local defects that can appear, like cracks, leakages, movements, that can appear at other locations where the equipment might not be present, and so it becomes impossible to localize and detect those events with the traditional sensors if they're not located at the right place. This is where distributed sensing offers a new possibility, because it's now possible to have a very long sensor that can measure every meter, and therefore it can sense everywhere and detect those defects and, more importantly, localize them. Distributed sensing has many possible applications. In general, it is composed of a measurement unit, for example, located along a river levee, and then a very long cable that can extend for several tens of kilometers and sense everywhere along that distance. Depending on the equipment that is used, we can measure strain and temperature, and therefore we can detect and localize changes in strain and temperature everywhere along the cable itself. So this is not only useful for river levee monitoring, but also to monitor dams, slopes, pipeline, large tunnels and bridges. So any structure that is very large, extended, long, can benefit from this sensing technology. We offer two main sensing systems called DyeTemp and DyeTest, and they allow the measurement of distributed strain and temperature together with specialized cable for distributed sensing as well. Typically we can measure with a spatial resolution of 1 meter, meaning that measurement is possible every meter, with a measurement range that can reach 30 kilometers. The systems are designed for long-term monitoring, so they are long-term stable, and we have developed, as I will show you, dedicated software packages for data analysis, management and visualization. This distributed sensing approach is a very cost-effective solution where a large number of measurement points are required. The functional principle is based on optical scattering in optical fibers. When we send a laser signal into an optical fiber, at every location along the fiber itself, a very small amount of light is scattered by interaction between the light and the material making the optical fiber. Part of that scattered light is backscattered and comes back to the source. If we now analyze the wavelength content of that backscattered light, we find that the original wavelength, lambda 0, that was sent by the laser, but we also find some new components called the Brillouin and Raman scattering components that were not present in the original signal and were created by an interaction between the light and the molecules in the optical fiber. And you will also notice that the position of the Brillouin peak and the amplitude of one of the Raman peaks are temperature and strain dependent. So we can use those peaks to analyze the strain and the temperature at the location where the scattering has occurred. We offer two instruments based on these two principles, the DyeTest system based on Brillouin scattering and the DyeTemp system based on Raman scattering. Now I've explained you how we measure strain and temperature, but how do we localize where we are measuring? This is very simple. We use a technique similar to radar, where light pulses are sent into the fiber, and then we listen to the backscattering as a function of time. And since locations that are further away from the instrument will provide the backscatter signal at a later time compared to those locations that are closer to the instrument. We can assign the distance measurement to a time measurement. So if we now combine the two information, Brillouin or Raman peak position and amplitude, together with the timing information, we can obtain a complete picture of the strain and temperature distribution along the sensing cable itself. So for example, if we have one location with a hot spot, another location with a strain peak, and another location with a cold spot, we can localize those locations and we can measure the temperature and the strain at this location and of course everywhere else. It is important to notice that the Brillouin system is sensitive simultaneously to strain and temperature, so it is necessary to separate those two effects by other ways that I will discuss shortly. Since today we are talking mainly about strain and deformation monitoring, the main system that we will be discussing is the DITES system. Based on Brillouin scattering, it can measure over 30 kilometers with a spatial resolution of 1 meter for close range and 2 meter at the further end of the fiber. It can measure with a strain precision of 20 microstrains and a temperature precision of 1 degree, with a measurement time of typically 5 minutes. Together with this instrument, we have developed an array of sensing cables that are used to measure strain and temperature. On the top left, you have the SMARTEC sensor. This is a composite patch cable, very flat, containing one optical fiber. So this is designed to measure strain on smooth surfaces. For example, it can be attached on concrete structure, steel structure, and other structures that are flat on the surface. On the top right, you can see a temperature cable. In this case, the fibers are free to move inside the cable, so they don't see any strain, and therefore they can measure temperature even when using Brillouin scattering. On the bottom left, you have the Smart Profile sensor. In this case, in the same square packaging, we combine fibers for strain measurement, so these are embedded into the plastic of the cable itself, and other fibers that are free in the red tube and are used for temperature compensation. And finally, we have the hydro and the geo cable that contains single mode and multi-mode fibers to measure strain with the Brillouin system and temperature with the Raman system. So this offers the best way to separate strain and temperature reading, even in the presence of very large strains. Another important part of a monitoring system based on distributed measurements is the graphical user interface. You can imagine if you're monitoring a very long structure that can be 30 kilometers long, it's impossible to observe all those measurement points manually, because you have 30,000 measurement points that are coming every 5 minutes. And therefore we have developed this software that on one side allows the automatic analysis of the data, so they can generate alerts in case of some thresholds are exceeded. And at the other end, they can show where those alerts are located on a map. For example, here you can see the red and the yellow dots locate the warning and pre-warning locations. It's also possible to segment the length of cable in sub areas, as you can see in the panel on the left, so that it's possible to immediately notice in which area of a plant or a dam the alert is being generated, and so different actions might result from alarms generated at different locations. And finally, on the bottom left, you can see an history interface where it's possible to look back in time, so you can see the evolution of the measurement previous to the current state. In general, when we are talking about measurement of settlement, sliding and movements, the main purpose of distributed sensing is to localize problem areas. For example, imagine a road where you have a potential landsliding area on top of it and a potential settlement area on the bottom of the street. So by placing a cable on the sliding area and placing another cable below the street in the settlement area, it becomes possible to monitor and localize those events. For example, if now a landslide occurs at this location, it will move the cable and elongate it, and in particular we will see ice trains at the beginning and at the end of the sliding zone in each of these paths. So in this case we will be able to localize the sliding area. The same applies to a settlement. In this case the settlement area will also create an elongation in the cable that we can detect. If we now look at the case of dikes and river banks, in this case we can combine temperature measurements and strain measurement to detect different conditions, including water overflow, leakages, settlements, and other movements in the dam. So again, by locating the cable at the appropriate location, we can identify and localize these issues well before they become dangerous or problematic. In the case of gravity dams, sensors can be placed at different levels in the dam itself or inside vertical boreholes, again to measure strain caused by changes in the concrete, for example, changes in load, apparition of cracks, and temperature sensor can detect seepages and changes of temperature due to solar radiation, summer and winter changes, and so on. Very similar approach for arch dams. In this case, one of the most interesting aspects is the monitoring of joints, and distributed strain sensing cable can be installed in inspection galleries or on the surface. So now, in the second part of my presentation, I would like to share with you some application examples to monitoring of levees, gravity dams, and the sinkhole area. The first example is a pilot project that was carried out in New Orleans by a consortium formed by GeoComp, the New Orleans Levee District, Shannon and Wilson, and SMARTEC. The purpose was to demonstrate the use of different advanced sensing technologies to allow a safer operation of the dams themselves and early detection of any possible disturbance to the dam itself. In our case, we were involved in installing a strain and temperature sensor in this test section, in particular on the I or T wall section, where a strain sensing cable has been installed on the top of the wall itself, and two other lines were embedded in the earthen levee on the dry side of the levee itself. So this system was designed to detect the leakages that would occur below the wall itself, and also abnormal movement of the wall, of the eye wall itself. In this picture, you can see an example of result we had in the first days of monitoring. In this case, what we see on the vertical axis or in the color is this measured strain, and on the two horizontal axes we have time in one direction, and we have also the position in the other direction. So the cycles that you can see on the time axis correspond to the day and night variations, and the changes that you see along the levee itself correspond to the movement created by the expansion and contraction of the different panels making the wall, and movement of the joints in between. So when the wall expands, the joints compress, and vice versa. So in this case you can, for example, see some days that are very hot and some days that are colder, and the amplitude of movement is less, and you can also see that most of the joints behave in the same way. So we can say that during this period nothing strange has really happened on that section of levee. So again, this is an example that shows the density of information that you can obtain with a distributed monitoring system, where hundreds of thousands of points can be monitored with a single measurement cable. A second example is the Ikdijk test bed in the Netherlands. In this case, we are talking about an earthen levee that was instrumented with different type of sensors, and in particular our partners Tenkate and Inventec have installed a distributed strain sensor in the levee itself to see if during failure they could identify the failure location. As you can see in this slide, this is the end state of the test, where a large part at the center of the levee has failed and create a very large settlement in the center and a very large movement of earth towards the dry side of the levee. If we now look at the measurements that were obtained during the test, we can see the 4 lines, the top, medium and bottom lines of strain measurement, and the color coding corresponds to the level of strains that were recorded. And as you can see, there are red spots located close to the beginning and at the end of the sliding zone, and so it's possible to localize the event itself. What is very interesting to notice in this case is that the first sign of ice strains in this area were visible already 42 hours before the dam failure itself. And since in this experiment the failure was somehow accelerated, it is a nice indication that precise distributed strain monitoring can really be used as an early warning system to localize and detect such an event, so that maybe it's still possible to do some corrective actions to prevent the failure itself. Let's now switch to a concrete dam that we have instrumented in Latvia. This is a very old dam with concrete in relatively bad condition, and in the past cracks have formed in the concrete and have caused leakages that have led to inundation of some of the internal galleries that are used for inspection. And so the owner was interested in a monitoring system that could detect the onset of those cracks, so that again corrective actions could be undertaken before it really became a concern. The dam itself is 250 meters long, and there is no indication of where the next crack might appear, so it was again a very good application example for distributed sensing. In this case, we have used the SMARTEC that was attached every 2 meters on the floor of the inspection gallery, so that if a crack would traverse it at some location, it would experience a peak of strain and generate an alert. So 250 meters of SMARTEC and temperature sensing cable were installed, and an automatic and remote warning system is in place to detect any new crack. Finally, an example. This is not a dam or levee, but it's a close application. Here, the purpose of the monitoring system in Kansas was to detect the onset of sinkhole. This is an old mining areas, and sinkhole have formed in the past, and since there are some roads or railway lines that cross that area, it's important for the authorities to have an early warning system if a new sinkhole would form, so that the traffic can be stopped and other measures can be taken. Here the approach was very simple. A trench was digged, and smart geotext with the smart profile sensor inside was installed in the trench itself and then buried, so that if a sudden settlement was created by forming sinkhole, the cable would sense an increase in strain and can generate an alert. In this picture you can see the graphical user interface that also shows the path of the sensor. It goes along a railway line, it goes along a street, and it covers an inhabited area with some houses. You can also see some of these circular shaped formations are previous sinkholes that have formed in the past. Now everything is green, so it means that there is no ice strain detected, but in case of new sinkhole, points would turn yellow and red, and alerts would be fired off by email so that it's immediate obvious where the sinkhole is forming, and emergency team can be dispatched to the area. Here you can see a very simple test that was carried out to simulate such an event. So by moving vertically the cable, we can introduce additional strain, and as you can see, when the cable is moved by 6 inches or 1 foot, we indeed observe strain peaks, in this case, for example, at 310 meters from the beginning of the cable, and so we can localize that strain location. You can also notice that when the movement is increased, we don't really see a large increase in the strain, but rather the strain is distributed over a longer and longer area. So this means that basically we are pulling the cable out of the ground over a longer and longer area, so it's possible to continue monitoring without breaking the cable, even if very large strains are applied. So in conclusion of my presentation, fiber optic sensors are an innovative but well-proven technology that is useful for structural and geotechnical monitoring and instrumentation. And some unique features of fiber optic sensor, in particular distributed sensing, open new application possibilities. Those distributed sensing systems offer an ideal solution for the detection and especially for the localization of new conditions such as leakages, settlements, cracks, abnormal joint movement, and other, so that they can be detected, localized, and people can act immediately on those new conditions. And with the application examples, you have seen that there are real-life, worldwide success stories where the system is permanently installed and used for detecting deformation, strain, leakages, and other movements. And with that, I thank you for your attention. And if you would like to ask any question, you can use the question panel that you have on your right, and I will be happy to answer those questions if you have any in particular. Thank you for your attention, and bye-bye.